The bar magnet. The bar magnet has two poles. These poles are North Pole and South Pole. The region around the magnet in which it exerts force on other magnets and on the object made of iron is called a magnetic field. We can scatter iron filings in the region. The iron filings tend to line up and form chains. The orientation of these chains indicates the direction along which magnets line up. The iron filings became little magnets by introduction. Magnetic lines of force. We can visualize electric field with the electric lines of force. Similarly, we can also visualize magnetic fields by magnetic lines of force. The path followed by the north pole of a test magnet in a magnetic field is called a magnetic line of force. When we can draw lines of force due to a bar magnet, we find magnetic line of force emerge out from its north pole and converge into the south pole. We know that electric lines of force emerge out from positive charge and converge into negative charge. If we place a magnetic compass in a magnetic field of a bar magnet, the needle of compass aligned along the lines of force. Properties of magnetic lines of force. 1. These are smooth closed curves which start from North Pole and on to the South Pole outside the magnet, and they move from South Pole to North Pole inside the magnet. 2. The tangent at any point on the lines of force gives the direction of magnetic field. 3. They never intersect each other. If they intersect, it means the field has two directions, which is not possible. 4. Magnetic lines of force are straight and parallel in a uniform magnetic field. Magnetic dipole and dipole moment. A pair of poles of equal and opposite strengths separated by some distance is called magnetic dipole. A bar magnet has two poles of opposite kinds, therefore it can be called as a magnetic dipole. The magnitude of dipole moment is a product of the pole strength and the separation between the poles. M is equal to M into 2L. Inverse square law of force in magnetism. Let us consider two magnetic poles of strengths M and M' separated by a distance R. The poles of strength M' is the field of pole strength M. The force between them is F is directly proportional to M' by R square. F is equal to mu naught by 4 pi M' by R square. This is the inverse square law in magnetism. Magnetic flux density B. The force experienced by a unit north pole at a point in a magnetic field gives magnetic flux density B at that point. A north pole of strength M is experienced a force F at a point. Force experienced by unit pole is equal to F by M. B is equal to F by M. It has unit Newton per ampermeter. It is a vector. Magnetic flux density at a distance r from a magnetic pole of strength M is given by B is equal to mu naught by 4 pi M by R square. Magnetic dipole in a uniform magnetic field. Consider a magnetic dipole of length 2L. each pole strength M placed in a uniform magnetic field B bar. Let the magnetic dipole moment M bar makes an angle theta with magnetic field B bar. Each pole experiences a force equal to mb and in opposite lines of action. These forces constitute a couple. Then, moment of couple or torque is given by tau is equal to F into Sp from delta SNP sin theta is equal to Sp by 2L. Sp is equal to 2L sin theta is equal to mb into 2L sin theta is equal to m into 2lb sin theta. Tau is equal to mb sin theta. In vector form, tau bar is equal to m bar cross b bar. If theta is equal to 90 degree, b is equal to 1, then m is equal to tau. The magnetic moment of a bar magnet is numerically equal to the torque acting on the magnet when it is placed in a uniform magnetic field of unit induction at right angles to the direction of the field.